That's part of the problem. There we go. There we go. I was only on Twitch. My bad, Twitch. My bad, YouTube. My bad, Twitch. Um, that's. I'm gonna take a note for that one. That's my bad. I was worried about focusing on the engineering part. I didn't answer the YouTube part. Anyway, question for you guys out there in the chat. What is the one thing that, if removed from a parallel circuit, would cause the circuit to stop working? Not all at once now. Sonic Bros, welcome to the stream. I don't know if you meant to delete your message, but what is the one thing that removed from a parallel circuit would cause it to not work? There we go. Oh no, I caught myself later on. I caught myself later on. Thank you, Skull. I sometimes forget to hit start on stuff. Welcome in, Krim.
What's up?
Would you like to answer the first question of the stream today?
Oh, what's that question?
What is the one thing that, if removed from a parallel circuit, would cause it not to work?
The power source.
Exactly. Thank you, Krim. Got our squad of geniuses out here today.
That's like asking if you what do you need to remove from noodles to make it not noodles?
Welcome in, Elliot.
Like you can remove flour, it turns it into something else. It's not noodles. You can remove the water. You can remove a lot of things. Or you can remove one of the branches in the parallel circuit, because then it's no longer parallel.
Incorrect. And I'll show you why. So, bringing up Krim's point about removing a branch from a parallel
I don't know what
circuit.
they're called. I feel like they would be cool to call.
No, you're correct calling them branches. You are correct in calling them branches, but that doesn't necessarily mean that the circuit won't work. So,
I mean, it'll still work, but then it's not a parallel circuit.
Which is the part I'm saying is not necessarily true. So I'm gonna draw an example up on the screen. So let's say we have a parallel circuit. Give me 4 numbers between 1 and 20.
2.
Okay, we got 2. So we got a 2-volt power supply.
Not a very big power supply.
Most stuff runs on 3.3 volts anyway.
Ah, that's fun. Hold up, so what would 20 volts do to something?
Probably start a car. It really depends on the circuit you're trying to work with. Because people hear 20 volts and they're like, oh my gosh, it's a lot. Then you realize that your wall is 120 volts, and it's really not even 120 volts, it's actually 169 volts, but it's averaged out to 120 volts.
Stick a fork in it.
Do not stick a fork in your sockets.
Oh.
I'm not getting sued today. And then you also think about, like, most power transformers in substations handle 400 volts, 500 volts, 1,000 volts, 2,000 volts. You have tasers that can deliver, like, I think 4,000 volts.
Chris.
Yes.
If I'm not mistaken, it's amps that'll kill you, or unalive you, not volts.
That is also partially incorrect. But we'll get to...
Incorrect?
Partially. We'll get to that.
We'll
get to the reasonings in a minute. But give me a couple more numbers. Give me like 3 more numbers.
Well, I hope I'm not the only one. Well, I'm not watching it because I have homework to do.
You're good,
I hope
bro.
there's other people watching your stream.
There's some people.
I'm not the only person giving numbers.
Elliot, give me a number. 8 and 14. Okay, 8 and 14. So we got 8, 14. Give me one number, Elliot. Got an 8 ohm resistor.
Chris.
Yes.
Also with that, if you if I'm not mistaken, I watched a video kind semi-explaining capacitors. If you do put a capacitor between the main part of the parallel circuit and the battery, then you can have it going for a little bit longer, despite having removed the energy source.
Yes, that's correct, and I'll get to that, and I'll also get to that in a few minutes. So, yes, that is true, Elliot. So let's say we have this circuit here. We have the circuit here on the we have a 2-volt power supply, an 8 ohm resistor, a 14 ohm resistor. I gotta make sure I use my units. Remember your units, chat. And a 9 ohm resistor. So if I were to run my circuit here, I would have to analyze the circuit. The first thing we're gonna do is we're gonna figure out how much total resistance we have in the circuit. And the way you do that in a parallel circuit is you have your R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3 all over RT.
I don't care about your screen share, Skull. I care about
think.
Chris's screen share.
I think this is it.
Alright, so the total amount of resistance is equal to those fractions over the total amount of resistance. How does that work? Doesn't that just create a paradox?
Hold up, let me consult the textbook.
By the way, you're allowed to just straight up keep the textbooks after, right?
Oh yeah, I bought this. I bought this stuff, bro. Let's see. Conductance, resistance metric units, thermistors, varistors, resistance circular wires, wire tables, page 60. I'm not saying that number. Resistance, great. Let's see. So according to the textbook, let's see. We got something. You can find the resistance of certain wires and blah 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 blah. I'm not going to talk about that because that's like deeper into electrical engineering than I want to dive into today. Let's see, semiconductors. No, we're not talking about semiconductors or insulators. Temperature coefficient of resistors. See how complicated this stuff can get in just like one day?
Yeah.
Let's see, you have metal film, you have metal oxide, you have aluminum. You have a lot of resistors you can use. Let's see, maximum voltage rating.
You know, gold is a really good wiring, I think.
Oh yes, gold is one of the best wirings. Gold is one of the best things you can use for wiring. Resistance, metric units.
But copper is used because it's cheap.
Compared to gold, yes. I'm just gonna look this up on Google because I'm looking through the textbook and I don't have time to search through the whole textbook. Chat, use your textbooks. They have most of the answers.
You know what else helps? Table of contents.
I used the table of contents and it wasn't there.
Let's just assume this is just like your standalone copper wiring.
Resistance formula. Resistance in parallel. Oh, that's right. I was almost there. I was almost there. Power lines made of gold, dude. Do you realize how many people will cut down power lines just to get some extra gold?
Dude, man.
My bad. I messed up the first part of the equation.
Ooh.
There we go. That's the equation. 1 over RT is 1 plus 1 over the total resistance is 1 over R1 plus 1 over R2 plus 1 over R3 and blah blah blah, blah so forth and so on and so forth.
You know, I would be taking notes if I wasn't doing a different kind of homework right now.
Yep. I'm not sure if gold wires would be better for for power lines, even if people didn't loot them, because gold has a lower melting point than copper does, if I'm not mistaken.
No, you're not. Dude, gold melt has a really low melting point.
It's also a lot softer than copper. So if you were to have anything run into a power line, you could severely damage it a lot easier than with copper lines. But anyway, back to the resistance question. So our first resistor is 1 over 8 plus 1 over 14 plus 1 over 9, and that equals 1 over total resistance. So if we gotta get these, we gotta get all these numbers in the same denominator. And we don't have a common denominator right now, so we're just gonna I'm just gonna use a calculator and convert these to a decimal number because I don't feel like doing extra math. But trust me, it's the same process. So 1 over 8 plus, so this is like 0.125 plus 1 over 14. Wait, hold on. 1 over 14 is 0.0714.
Yeah, Chris, I got finals this week.
Dude, I wish you well, my dog. That's kind of funny, Elliot.
There's like 3 classes that I could just like not do, and like I could write my name on it and I'll still pass with above a C.
And that's the goal. That's what you want to do in school. Be so far ahead that you could literally just show up and pass. So we got all these numbers, so we're going to do this plus 0.125 plus 0.0714, and we get 0.3, so we get 1 over RT equals 0.307, if we multiply that by 100, well, if we do our RT is equal to 0.1 over 0.307, so 1 divided by 0.307, you get the total resistance in the circuit. I gotta scroll down, I gotta remember to scroll down. Total resistance in the circuit is 3.257 ohms. Now, you might be thinking to yourself, what the heck? Why in the heck is the resistance so low? Don't I have a 14 ohm resistor in the circuit? And don't I have an 8 ohm resistor in the circuit? What the hey, dog? That don't make sense. Well, it actually does make sense, because in a parallel circuit, you cannot have more resistance than the lowest resistor value. Let me also pull the Discord back up, because I know there's some stuff in the chat. In parallel circuits, there cannot be higher resistance than the lowest resistor. Now that means if I have like a 1 mega ohm resistor, which is 1,000,000 ohms, and I have a 10 ohm resistor, the total amount of resistance in that circuit can't be more than 10 ohms. It sounds ridiculous, but if you think about it, when you have 1 over 1,000,000 and 1 over 10, and then you do 1 over, and then you know, divide out by that, it's still not going to be 1 over 10. So that's how that works. Or it's not going to be greater than 10. So, to go back to what Krim was saying about like parallel circuits, if you remove a line, well, if I remove this line, say I remove the 8 ohm resistor, I still have a parallel circuit. I still have a circuit that is tied to ground. I still have a resistor, and I still have another resistor, and I still have a circuit that's tied to ground with a power supply going through it. Also,
by the way, what's the symbol for a capacitor?
Oh, a capacitor symbol. You can draw that.
Yes.
Like, it's not. I know how to draw it. I'm just like trying to find a place to draw it. just like that.
Put it in between one of so it looks like a miniature version of the battery.
Yes, it's actually so common that people mistake batteries for capacitors that they added that second line. That's why if you see a battery drawn in a circuit or on like on a schematic page, they'll draw the battery. So this is just like a little side note thing that if you go into any electrical field or if you have to learn any electrical theory of anything like that, this is just a little side note to help out with your drawing so you don't get points taken off for dumb mistakes. Batteries typically get drawn like this, and capacitors are typically drawn like, well, like this, obviously, like I just drew. But some people, the weird people, draw batteries like this. And why you would draw a battery like that, you're weird. Just draw it like a normal person and add the extra stuff so people know that it's a battery and not a freaking capacitor. Because you get someone with bad enough handwriting.
If I'm not
like
mistaken,
myself,
capacitors discharge energy much quicker than batteries in some cases.
Yes, that is completely true. Capacitors have the incredible ability to rapidly disperse charge. That's one of the main reasons why we use capacitors. Batteries have the immaculate ability to hold a charge and release it over a controlled period of time. But to go back to the basics, so that way we don't leave too many people behind, because this is supposed to be just for beginners. But like that was just like a little tidbit side note for things. So if you
Hey dude, I've never gone into electrodynamics.
Oh, I'm not talking about electrical dynamics. I'm talking about electrical engineering.
Electrical engineering, my bad.
You're good.
By the way, quick question: do you have to get into thermodynamics with engineering?
Depends on the one you go into. If you go into engineering for like mechanical or chemical or civil or construction, a lot of times you'll have to go into thermodynamics because you'll have to deal with the different types of materials and how they reflect, how they absorb heat, how they disperse heat, how they accept current flow and charge and conduct and all that stuff. Like bunch of stuff. But I don't remember doing much thermodynamics in electrical, so I would say no for electrical.
Did it ever cross your mind that it was interesting?
Somewhat. I just never understood it. But yeah, so to solve this first circuit right here, does anyone have any idea how we might solve this first circuit with this value here? How will we solve this circuit for the current flow that's going through it? We're trying to solve, so just a little miniature refresher, just a miniature refresher from about 15 minutes ago. We have Ohm's law, V equals IR. I is current, R is resistor. I should also probably like define these letters.
Probably divide your voltage by the resistance.
Hold on one second. Let me write these out, because
or multiply if it's a fraction.
I recognize that I may have confused some people. This is voltage. Because
yeah, V can be velocity as well if you're in physics.
Exactly. Electrical engineering letters make no sense. This is current.
I prefer physics. Wait, I is current.
R is resistance.
Oh, yeah.
And their symbols. Voltage is a given. Elliot, what's the symbol for voltage? I'm looking at chat. Don't overthink it, Elliot. You got this.
Dude, I am, in terms of school stuff and like mathematics and that stuff.
It's all good, Elliot.
Like,
yes,
I don't
correct.
really care much for the stuff they teach in school, but in terms of this stuff, like the more complicated stuff is what I like.
You'll thrive in like the engineering field, or like if you go into like any after what's it called
Dude, I'm
you said
planning
you want
on
to go to
doing
NASA,
astrophysics.
yeah, you'll thrive in that. Okay, so I guarantee you none of you are going to be able to guess the symbol for current. Absolutely no one's going to be able to guess this. Just throw something out there. Everyone throw something out there.
By the way, what application do you use for the writing?
OneNote.
OneNote. All right.
It is not E. Well, it is not a C. It is not a C.
What is C in electrical engineering?
Usually capacitance.
Huh.
Elliot, you're correct. But we actually use a capital A most of the time. What the heck did I just freaking... No, take that off. There we go. Most of the time we use a capital A.
So what would be lowercase a be then?
I don't know, but it gets confusing because of it gets confusing between other disciplines when you use lowercase a. Yeah,
so it's
a for amps.
situational. Amps, yeah, ampage.
And then no one's gonna be able to guess the letter for resistance because it's not even English. It's an omega symbol because it's ohms. Don't ask me why they decided that ohms was omega, but I like it. I love the letter. I love the letter omega. I love that letter. So,
that's what if I'm not mistaken, is that what's it called? I know what it's called.
The Greek symbol?
Yeah, Greek.
Yes, it is Greek. Okay, so we know voltage. So now that we know the symbols, we know voltage equals current times resistance. So if I'm looking for current, now you guys can do this on your own, and I know this is going to be a video at some point. So I'm going to draw the equation out, and I'm going to give you like 5 seconds to pause, and then like I'll talk through the answer as we go.
Chris, may I speak what I believe it is going to be?
Give me just
or at least what you're gonna do.
Give me 1 second to draw the equation. So I want the current. Oops, that's a really bad eye. I want the current. Oh, I need to scroll down further. Okay, I want the current of this circuit. What is the current? The total current of this circuit. What is the total current? Hey YouTube, if you're watching this back in 3.5 years because you're trying to pass your electrical engineering basics class, welcome in. You have 5 seconds to solve. Or pause.
Alright. Wait, where's the... Okay, so...
Alright, great. Your 5 seconds have passed, and hopefully you get a pause.
Alright, I think I have an answer.
I'm going to talk through it, just that way we stay on top of it, and I don't miss anything. So the first thing we're going to do is since I'm asking for the total current, it's important to recognize that you're not looking for the current through a certain node. Sometimes they'll ask you for the current through a certain node. Do I remember how to do that right now? Honestly, no, I don't. So I'm not going to do that right now. But since I have I total, I'm going to take R total, and that was 3.257 ohms. And my voltage in the circuit, which is 2 volts, and if V equals IR, then the way I would solve for current is I would just divide by R on both sides. So now I have 2 volts over 3.257 ohms. And then that would be calculators to the rescue. 610 or 614 milliamps. Now you might be thinking, well, why didn't you just write it like 0.614 amps? Because most of the time in electrical engineering you're going to be dealing with milliamps. Sometimes you'll get to microamps. If you're over an amp, you're probably dead. Which leads me to the next thing about electrical engineering is current is pretty dangerous. Current can be dangerous. But why can current be dangerous?
Lack of current? Do you say lack of current can be dangerous?
No, I said current can be dangerous. But the question is, why can current be dangerous?
Because it carries amperage, obviously.
But what does that mean? Think about it for a second. What does that really mean? Why is it that me having a 1.5 volt battery...
Can I eat it?
Like, why is it if you have a 1.5 volt battery, if you put that in a bottle of water, you probably won't die? It's actually not recommended. Don't put a battery in a bottle of water. That's a really bad idea.
You know, trust me, it's not that bad. I've done it before.
I would recommend against it. You know, that would be something where if I wanted to make a grenade, I would put a, hypothetically speaking, of course, on YouTube. Hey YouTube, don't do. But if I were to hypothetically want to create a grenade, I would throw a lithium-ion battery into a bottle of water, and then I would just toss a bottle of water at somebody. You know, never done that before, so I don't know the outcome. But it's typically not a great idea. But
does it have to do with the energy in your brain?
It is not the energy in your brain. It's actually in reference. It depends on the reference of how much resistance you have in your body to it. So like so just as an example, I'm just gonna look this up because it's easier to look this up for anecdotal evidence. How many volts does a taser emit? A taser emits a peak voltage of around 50,000 volts when initially activated. So you got 50,000 volts from a taser. You got 50,000 volts from a taser.
You ever been tased?
I have not been well, yes and no, but not really.
Have you ever been, have you been tased by your own choice?
No, I've never been tased by my own choice, and I've never been tased by
I feel like I'm the type of person that's just like, I wonder how it feels.
And then I'm going to put up what is the resistance of human skin?
Probably not unbelievably high.
I can't remember every time. The average resistance of dry human skin ranges from 1,000 to 100,000 ohms. So we're going to say probably 100,000 ohms in the parts where you would probably get tased. So we'd say 100,000 ohms. That gives you basically 5/10, which is 1/2, and that's half an amp.
My English teachers don't know I'm secretly putting math symbols in whatever I write.
You need to push through the body until drastically Yes, yeah, I can, Elliot. But see, half an amp. I'm not doing Cuphead today. I hate to break it to you, but I'm not doing Cuphead today. Sorry about that, homie. We're doing electrical engineering.
This is what this and Subnautica is why yeah. Amazing.
But yeah, so we have a half amp going through your body with 50,000 volts of electricity running through the 100,000 ohms of resistance to your skin. Now, in general,
how much resistance is 100,000 ohms?
It's 100k, 100 kilo ohms. I don't know if that's the question you were asking. Lethality chart.
Now, did you have to deal with joules at all in electrical engineering?
Yes. Tons of joules.
We love joules.
But they're not very valuable.
Yeah. So I heard, but we still love them.
Or amps human reaction chart.
Chris, have you ever seen a picture of a 3rd degree or a sulfuric acid burn? It is not good looking. Pretty gnarly.
I have not.
Chemistry can be very scary if done.
Man, Elliot, I appreciate that. Okay. How... Sometimes when you look stuff up on the internet, it doesn't like to answer... doesn't like to answer the question you're trying to ask. How many amps to kill a person?
You're gonna be put on a watch list for
They can
that.
put me on as many watch lists as they want to put me on. I'm gonna run that current through them. That's a joke. That's a joke.
Yeah, it's a joke. Also, hi Elliot, I cannot see your text, so I won't be able to know.
How much current can anybody withstand? Blah blah blah. Something, electric shock. Something. Okay, here we go. Perfect. This is the chart I was looking for. Gosh dang it. This is the chart I was looking for. So at 1 milliamp, you know, that's like you shock yourself on the door. You know how you be walking through the hallway at your house, and then like you walk past a piece of metal, and it's like, ah, dang. That's about 1 milliamp.
Static electricity.
Yes, like a static shock. 5 milliamps. You get a slight shock, felt disturbing but not painful. Most people will let go. But strong and for like you know that's like a you rub your socks on the carpet, and you go up to your brother and be like, Phew! And he's like, ah, dude, what the heck? And like that's like that involuntary response. You built up enough charge to create 5 milliamps of current. So from 6 to 10 milliamps, you get a painful shock. That's like your muscle controls is lost, and this is where like you might not be able to let go. You know, you're like like you know that's a so that's the thing. 50 to 150 milliamps, you get extreme pain, respiratory arrest, severe muscular contraction, and individual cannot let go, and death is possible. That's like you stick your hand in, or you stick like a fork or something in the electrical socket when you're because you can't, you physically, your neurons that cause that electrical signal in your brain that cause you to get like your that cause your muscles to fire, because believe it or not, the God I believe in was smart enough to run stuff off electricity billions of years ago. You know what I mean? So the only problem with that is that when you mix electricity with electricity, sometimes you get too much electricity and you overload the electricity with the electricity that you added to the other electricity. Make sense? Great. At 1,000 to 4.3 thousand or 4,300 milliamps, that's like a full amp. Your ventricular fibrillation and uncoordinated pumping of the heart, that's what they use. That's what they use when they shock your heart. When you get, we're like
defibrillators,
clear, like that big kick to the chest, where like you know.
Fun fact: I am CPR certified.
Awesome, that's great. So you know about this. So you know they do the thing. Clear.
Yep. You have to be doing CPR before that, like.
Yeah, you have
for
to do
a good little bit beforehand. Like, that thing is a last resort if you do not resuscitate them.
Because it literally will stop your heart.
Yeah,
it will
or
literally
restart.
Stop your heart. The only thing that restarts your heart is your brain like, hold up a second, we're supposed to be beating that thing. Okay, let's do it.
Fun fact, there's an armband some people have that means do not resuscitate. If you resuscitate them, you can get sued by a lot of money.
Yes, the percussive maintenance on the human body.
That's why I'm adamant about, like, if someone else will do it, I would much rather them do it instead of me.
I like the meme that that Skull put in the Discord. I like that. That's a pretty good meme.
Explain it to me. I am looking at your screen right now.
Let me see if I can pull this over. Low voltage. I always take the path of least resistance, and I cannot pass through anything unless it's the conductor. High voltage. Arcs through the air. The reason that's funny to me is because at high voltages you can actually break down the resistance of air. Air does have resistance.
Well, yeah, it's made of normal particles.
And I'm not talking like air resistance, like planes flying air resistance. I'm talking like it has like an ohm resistance level. In the millions. If you don't believe me, take a multimeter, turn it on, and put both probes in the air, and then see how much it reads. But anyway,
You know, I would if I had one on me. I know my parents have one. It's in the garage, but still, I would if I had access to it.
Fair enough. But yeah, so anyway, at 10 amps, you're basically cooked. You basically fried. That's like getting struck by a bolt of lightning. Like, that's like 10
People
amps.
have survived.
Exactly. It says death is possible. It doesn't say death is guaranteed, but it's
now
possible.
That's scary. Surviving lightning.
Probable. You know, one of my best friends has survived being struck by lightning.
Dude, Chris,
She's
that's
amazing.
like God tried smiting me down, but I survived.
No, I don't think it was like that. You know, she's pretty
I know.
cool though.
It's
she's
just
awesome.
funny. Like, if I was ever struck by lightning and survived, I would 100% just be like, yeah, God tried to smite me, but I survived.
See, I have this relationship with God where I was like, look, man, if you ever strike me with lightning, I gotta get lightning superpowers. I have yet to be struck by lightning.
You're not gonna become Flash.
Oh, no. I don't want to be the
What's
Flash.
What's one other superhero? I forgot what it was called. I only know him from the early Lego Marvel game.
Static Shock.
I think so. The dude who looks like he wears green, yellow, has like a star
Electro.
thing.
Electro.
Yeah, him.
Nah, like
I only know him because of Lego Marvel.
Look, all I'm saying is that the Lord hasn't given me lightning powers, so the world is safe yet another day. Because I don't think I'm ready to handle lightning powers. At least not responsibly. Like not as responsibly as like a true superhero would. But anyway, we're getting off track. The whole point of this was like about electrical engineering. We're getting off into like way off in electrical theory. This is more like a that was just like a thing about like how amps can be dangerous, and the reason why is because it'll break down not only once it reaches a certain point where the current flow is higher than your body can manage, your body's electrical signals will begin to start breaking down and cause your body to start locking up. You'll start having muscle spasms, or you'll start having your neurons won't be able to fire properly and release muscles, and it could potentially stop your heart. That's why that's why amps are dangerous. But current is not the only dangerous thing. Current is not the only dangerous thing. The other dangerous thing is voltage. Surprise, surprise.
Alright, so how many volts would it take for someone to unalive? That really depends on... Yeah. You know, I have some really interesting foil on me. I really don't think it's aluminum, or maybe it is, maybe it's not. But when I put a battery in it, it started to heat up like a lot. And like, I have this weird temptation to just like wrap it up and then just throw it. I know I shouldn't. Going to. I want to.
Well, if you end up doing it, let me know how that goes and how it works out. I would recommend against it personally. But anyway.
Yeah, I want to do it, but I shouldn't.
But anyway, high voltage is what actually will cook you. High voltage is essentially high energy. But you know what's not dangerous? You know what's not dangerous in excess? Or in excess? Resistance. Resistance is dangerous when it's low.
Explain.
So now I can kind of get to the idea of like how electrical engineering professors typically teach how electricity works. And this is how my mentor at my job. Shout out to you, because you hired me.
Ooh, that hurt.
See, I paid attention. He knows I paid attention because I obviously know how to do my job, because I would have been fired if I didn't know how to do my job. So let's say you have it's time to test the artist skills. Let's say I got this big river.
I think I vaguely know what you're getting at.
I got this big river right here, right? And let's just say I got a beaver. We got a beaver.
Are you gonna unalive the beaver?
And he builds a dam. And so now this river has basically stalled. So now instead of the river being flowing, we basically just have like a stalled river. Oh, hold up, y'all can't see it. Hold up. So we have the dam built up, and we have a stalled river.
Yes.
But let's say the dam springs a leak one day. Boop. Now, how hard is the amount of water doesn't change, right? The amount of water doesn't change. But how much is this water going to be pushing out of this dam? You might have like
what's the volume of water?
You might have like a high pressure point at the very epicenter, but you're basically just gonna have like a little trickle. You know, you might have like 100,000 gallons of water. You're gonna have like a little trickle coming through the small little hole in the dam. It's not gonna do too much damage. Yeah, but your hand's gonna get wet. Yeah, it might wear away at the dam a little bit more each and every day. But long story short, you don't have much damage. So this is high voltage, high resistance, low current.
HV.
So we would call this like to hyphenate it or acronize it. To acronize it, you have HV, HR, low C, or LC. HV, HR, LC. If I were to have, can I zoom in? There we go. If I were to have another dam where like I have a lot less water, let's just say I have like, a small like bucket of water. Let's just say I have a bucket of water.
5 gallons? Sure.
And I were to pour that water out immediately.
Like no resistance. Or minimal.
Onto...
If you're going upside down.
Onto... Oops. Hold on. Let me slide this over. Onto somebody's head.
Well, you're going to have one angry person.
This is no resistance, or this is low resistance. LR. Low voltage. Because 5 volts is not that many volts. Low voltage, but high current. So, dude's probably going to be a little bit mad. Pressure isn't necessarily applicable in electricity in the sense that water is, but it's a little bit different. But if I were to take like, I don't know, a swimming pool.
No.
Where is it? Come on. Come on, thingy. Update.
Are you gonna
time.
crush someone with water from a swimming pool?
You'll see. This is not wanting to update. Give it a second. It'll update eventually, I think.
You hope.
Oh, that is not the pin that I thought it was.
Hey, it's me.
Just gonna... So we have a swimming pool, right?
Yes.
Yeah. Hold on. Let me turn this VPN off. This one NordVPN is like okay, but not great. Not sponsored yet, but once I get sponsored, it's gonna be the greatest thing I ever had. You know.
Dude, in terms of VPNs, I use Proton.
Pause.
It's free. It works.
Disconnect. There we go. We're just gonna draw it with the mouse for now, until it decides to catch up.
Wait, you have a drawing tablet?
No, I just have my iPad that is mirroring the screen basically. I have OneNote open on both places. If I actually... If I close this and reopen it, will it resync? Oh, there we go. Now I can erase this.
Or make it 3D.
Now we're just gonna erase that. Okay, so now we have a giant swimming pool. So this would be high voltage, and then we rip a giant hole in the side of it and throw little Timmy here.
Dude, you're a child? No.
All this water is gonna come rushing out.
Chris, quick mention. If a river is high voltage, wouldn't that make a swimming pool more of a medium voltage?
It's all relative.
Well, yeah, I suppose you're right.
So you have high voltage, high current, and low resistance. And that comes down to
Or little Timmy.
somebody being on the wrong side of life.
Or Timmy.
Or in a less extreme case, if you have a water hose, you got a little water hose, but
Now here's the point
you're
where
spraying this water hose into you're putting this water hose into a pressure washer. So now you have like a huge high pressure situation here. This is high current, high current, high resistance, but low voltage. I think that's how it would work. Because you're restricting the flow, that would increase the resistance. You have a
seems
high...
like it.
Well, actually, it would create. You may have a low voltage here, but you'd actually have a high voltage here. Anybody want to take a guess at why?
Because it acts more like a transformer, the nozzle.
Not necessarily that it's a transformer, but that when you're increasing the resistance, if your equation, remember, is V equals IR. If my resistance here, so let's say I have like 2 volts here. That's because my current flow is like 1 and my resistance is 2. But then if I bump my resistance up to like 50 and my current remains 1, I now have 50 volts. That's where it gets dangerous. So like when you're dealing with like 1 amp of current and stuff like that, 1 amp is a lot of amps. But if you can multiply that by like, if you get like 1 amp multiplied by like 0.2 volts, you only get 0.2 volts out of it. 0.2 volts at 1 amp, it's not that bad. Anyway, any questions? Any questions related to this right here?
The moment you upload this to YouTube, send me the link.
It's already, I mean, it's uploaded. It's just gonna have to.
No, I know.
But any questions on like the basics so far?
Now, can you kind of explain how, I know how the capacitor works, but can you explain how it works in like a computer? Because I know computers tend to have capacitors, from my knowledge.
Well, that's a little bit more tricky. That's a more complex answer than most of us are ready to get into, and it's going to take me a while to actually explain everything leading up to that. But the short answer to that is it's essentially a way for it to measure logic. It's essentially a way for it to measure logic, and it's a way for it to store power in the case of a power failure. So like if you get if like the power goes out in your building, your computer won't immediately die. You have like 2 or 3 seconds where it won't just shut off completely. So if you were here a couple weeks ago, when we had that big thunderstorm, or I guess it was a couple months ago at this point, where we had the big thunderstorm and the stream was cutting off and it wasn't letting me stream Fortnite, and my computer shut off, and I was like, oh, my computer just shut off, but like it didn't like shut down. It's because the capacitors kept it breathing for just long enough for it to regain power.
Huh.
But the other part of it is that
so it's
it is a backup battery. It is essentially a backup battery, but it releases energy a lot quicker than a battery can. So capacitor can hold a lot of charge. Capacitor can hold a lot of charge, but it will also dissipate that charge quickly.
Stupid question, but what happens if you have a bunch of capacitors in sequence?
Actually, we can talk about that. So one of the other most basic electrical engineering principles after you get out of voltage, current, and resistance is how the different components react. Normally I would start with a resistor, but because Krim asked a question about it, we'll start with capacitors. So capacitors.
I think that thing is laggy.
There's a lot of capacitors. There's a lot of different capacitors out there. You have ceramic, foil, electrolytic, bunch of other ones. But essentially, they can break down into 2 categories. See, electrical engineering is really, really simple, but it gets really complex with the simple stuff you give it. You have your polarized and your nonpolar. Now, your polarized capacitors are typically your electrolytic ones. That's typically those. The non-polarized are the others. Take that with a grain of salt. I'm not going to go through all the capacitor types right now because that's getting into semantics and stuff. But polarized capacitors, they have to be facing a certain way when plugged into a circuit, or else they will explode. Because they're...
Huh?
Yeah, so polarized capacitors, if plugged in incorrectly, So let's say that this is usually the negative side and this is the positive side. You have to pay close attention to the polarity, or they will explode.
Is it because the different sides react harshly with the different charges?
It's not necessarily that. So the way capacitors work, this is just like a basic grouping of how of things to note of like polarized versus non-polarized. But the way a capacitor works, so let's break it down a little bit how it works. Y'all remember the show How It's Made? I think they still make that show.
Of course I do. I still watch it.
How it works. A capacitor.
Honestly, if you grew up without How It's Made, I feel so bad, bro.
Holds charge. AKA, say it with me now, a capacitance. A capacitance. That's how you can tell how much capacity a capacitor has. So a capacitor holds a charge, and it can distribute that charge quickly.
Chris, you ever lick a 9-volt battery to see if it has charge in it?
Alright, Elliot, have a good night. Hopefully this was interesting, and if you decide to watch it later, you don't get too lost. I'll try to keep it streamlined. What was the question?
Honestly, I'm grasping it pretty darn well, despite me like not like understanding really easy math.
Well, it's because I'm not going into math really. Like there's a lot of math that goes into electrical stuff, but I'm not really digging into the math because the math is something you'll go to college for, or something that you'll have to study when you go take the classes. This is the concepts to get you introduced to the equations that you'll have to solve for. So capacitance, they can, if I remember correctly, the capacitance equation is C equals di dt times R. I think that's the equation.
Question: what is D?
What is what?
D.
Derivative. You have to take a derivative. You take the derivative of current.
Times resistance.
I'm double checking my work real quick.
Wonders.
Oh wait, C equals Q over V. That is not correct.
What is Q?
Charge.
Okay.
Q is the magnitude of charge on each plate, and V is the voltage across the plates. Let's see, parallel plate. You can also tell the let's see, parallel plate capacitor. Capacitance is determined by the geometry and the dielectric material. So to get for like a capacitor that you'll typically see drawn in circuits. So like for one of these right here, that equation there is going to be C equals the area of the plate divided by the separation of the plates. So you have your area, so kind of draw it in 3D. You have your area of the plate, and then your distance between the plates.
Now, are we just talking about regular circuit boards with the plates?
No, we're talking about capacitors. We're talking about like the plate that makes up a capacitor.
So layers.
Yeah, so essentially a capacitor in layman's terms is two metal plates with some type of dielectric material in between. The dielectric material can be air, it can be copper, it can be
Ceramic?
hydro mesh, it can be ceramic. Yes, it can be a lot of different things. Excuse me.
Now, copper's conductive. What do you mean by dielectric?
Dielectric is just something that's put between two capacitors that's usually less conductive than the two plates that are opposing it. It's so that way electricity can flow between the two plates, because it's very hard for electricity to flow through air. You have to have a huge amount of voltage or a huge potential difference charged up on one side to basically arc across the other side. So having a dielectric material allows some of the electrons to flow through without dropping a huge arc across the plates. Now, if you short it to ground, you'll get an arc because you're shorting it to ground, but that's something for a little bit after this. So, okay, so I've explained charge and voltage. How?
Alright, Chris, I apologize if you hear echo. I'm in a very empty room right now.
You're all good. Q.
Because... I have to wipe down the ceiling of one of the rooms in my house because we're gonna be repainting it soon. And that room is going to become my new room.
Okay, so here we go. This is where I got that DIDT. This is where I got it from. So, oops. So, when electrical current flows for a specified amount of time, we can calculate the charge. Constant current is I times T. The DIDT comes for if you have an alternating circuit, like an alternating circuit. When there's a constant current, the time is 0, or the change is 0, so you have no voltage across a capacitor. There's not really a voltage across it when there's a completely consistent constant charge, because Q being broken up into I and T. So let me pull this back up over here. So if I have Q equals I times T, if my I is constant, like 1, the whole time, my charge is constant the whole time. So that's why you have that's why you can have a capacitor charge up in a DC circuit or a direct current circuit. And that looks like, so like to draw you an example, if you have a battery that's like 5 volts and it goes into a capacitor and it goes around and then it goes to ground, eventually doesn't matter what the capacitor charge is, eventually the capacitor is going to charge up to here. But it doesn't actually charge like that. It more so charges like this. It's no, wait, that's not right. That's not right. Charges like this. There we go. It has a huge rise time. It has a huge rise of spike at the very beginning, and then when it reaches steady state, which is like right about here, that's where it's basically 5 volts the whole time. That's where it's like sitting at 5 volts, and usually that's within 5 tau or 5 time constants. And then tau is actually determined by the resistance multiplied by the capacitance. If I'm no, it's 1 over square root of RC. If I remember correctly. I think that's it. Usually the time constant is less than a second anyway, so it doesn't really matter for our applications today. But just to let you know, like, please verify this and check it again, because it's been a while since I've had to do any of the basic stuff, so I'm forgetting things and skipping over stuff that I remember vaguely. So please verify, trust but verify. So that's a DC circuit. And the way a capacitor works, just in general, the way a capacitor works just in general is that when you have a so we're gonna like just blow this up. I'll blow this up so that way you can kind of see what's going on. You have on one side your I believe your anode. I'm pretty sure it's called the anode. You have all your positive charges building up here, and your cathode, you have all your negative charges building up here. And in between there is some type of dielectric material preventing them from just arcing across. And across all this is 5 volts at steady state. So with that being 5 volts at steady state, goodness gracious. With that being 5 volts at steady state, when you finally connect something to the circuit, so like let's say you have like a light bulb, this is gonna short. This is basically gonna call all the current into this wire, and then so like even if I were to remove the battery, if I took the battery out, since this is at 5 volts now, and this is connected to, oops,
still has 5 volts to distribute.
Exactly, but it's not a battery, so it doesn't distribute it over a long period of time. Because if we remember from, I think I said this last time, or I've said this before, if we remember, a battery just charges. This is like batteries. They discharge basically like this. Like it's not exactly like a falling loop like that, but batteries will either fall like batteries will either behave linearly, which is usually your double A's. They go to like, and there's like a cutoff point. Oops.
Is there any power storage mediums that behave exponentially when out or running out?
They don't necessarily perform exponentially, but this is like double A's, and then for your rechargeable ones, usually they'll start out like this. They'll ride, and they'll also fall off. But a lot of times we charge them before they die, so then they rise back up, and then they fall off, and then eventually they get down to 0. But you don't really want to let a lithium-ion battery get down to 0. And then their lifetime, over their lifetime, their battery life will look like this, and then it'll just have a steep drop off. And it's like this is like battery life over time. And we'll just say that like some years down the line, the battery life will be absolutely atrocious because the ions have worn out their energy, essentially. But yeah, so capacitors, they hold a charge, they distribute it quickly, and they're similar to batteries, but not exactly. So anyway, capacitors capacitors will release their voltage. So this is like a capacitor. It'll be charged, boom. Oops. It'll be charged, then boom. And that's about how fast it drops. almost a straight line. It's more so like this. But yeah, it's a very sudden drop. That's why it's very dangerous to charge capacitors up and then leave them charged, especially large capacitors that can hold like 50 volts, 100 volts, 200 volts, because it will literally just deliver all of that voltage like that. And current flow is the amount of energy changing over time. That's what current flow is the amount of energy changing over time. So with
that's like 0 to like 50.
That's like, you know how like in the drop tower, how like you're at the very top, and then all of a sudden just boom, you're falling. That's what a capacitor is like, that's how fast a capacitor will distribute charge. It's not like a roller coaster where you can like see the drop, and then you can feel yourself gaining speed, or it's not like a car where you accelerate to a certain speed and then you're just riding that certain speed. No, it's literally like a instant drop.
Chris,
yes.
Is there a way to trick a capacitor into releasing it slower? Or would other mechanisms be required?
You would have to rig it up with you'd have to rig it up with resistors and inductors to cause it to behave differently. But in general, capacitors will still disperse energy extremely quickly, much quicker than a battery will. Now, there are supercapacitors that can behave similarly to a battery, like they're in between a battery and a capacitor, but those are extremely dangerous and they can hold a lot higher charge, and they are very prone to fires and exploding if shorted together. So it's highly recommended not to short those things. So that's a capacitor in a direct current application. A capacitor in a alternating current, so like AC, you have a capacitor in a circuit, and if you recognize if you recognize that little symbol inside the circle, that looks a lot like a sine wave, right?
I cannot see it. I'm in a separate room.
Oh, well, we're gonna say it looks like a sine wave, and that means that it's going to. Everybody knows that a sine wave is the mathematical representation of what a circle is doing. It is starting at one point, it goes all the way around, and comes back to the same point, and then goes all the way around, and comes back to the same point, and goes all the way around, and back to the same point. So if we have a sine wave, don't know why.
Oh yeah, I know what you're talking about.
So if I have a sine wave, and
go up, down.
Exactly. If I have a sine wave, it goes up and down. Well, when you put an alternating current, that's essentially what's happening with the electrons. The electrons are all flowing. So I'm going to draw it in two places.
You know, whenever I hear electrons, I either think chemistry or quantum mechanics.
Well, now you can add electrical engineering to that, because that's literally what all of electrical engineering is. So on the uptick, we'll call it the uptick, all the electrons are flowing this way. Into this part here, and charging up here, causing a positive charge over on this side. And then on the downtick, all the electrons are flowing back the opposite way. So they're going this way now. into this side of the plate. And now you have all the electrons on this side and the positive charges on this side. And essentially what's happening is you're pulling the current back and forth, back and forth, back and forth to create a constant current flow across this capacitor. You're forcing a current to flow across the capacitor by basically causing it to run back and forth. It's like if you fill up a cup with, it's like if you fill a bucket with water and you pour that bucket of water in another bucket of water and you pour it faster and faster and faster. It looks like a stream of water back and forth. Like if you were to able to like switch them fast enough, it would look like a consistent stream of water back and forth, even though there is no actual running water. And so at high enough frequency, when you're switching back and forth quickly enough, you end up having a short circuit looking device across the capacitor. But in a DC circuit, since all the charge is charging up on one side, like I showed you here, in this circuit, in a DC circuit, let me label this as DC. And this is AC. Yeah. Since all the charges
stupid question.
Hold on 1 second.
Yes, sir.
Since all the charge is building up on one side here, you essentially have an open circuit here, and that's why a lot of times you can't really just put a capacitor in a circuit and expect it to work, especially when it's not tied to ground, because it's not really able to do anything. You have to put a resistor in circuit with it, so it'll have something to pull the other protons and electrons away from the capacitor. Now, what's your question?
So, what's it called? Is it harder or easier to short circuit a DC or AC current?
It depends.
If anything.
It depends. A short circuit. So I guess the next thing we can talk about is short circuits, because I could talk about. Well, actually, now I can talk about resistors, because you asked that question about short circuiting. So, scrolling down. London Bridge is scrolling down.
I love talking about mathematics and science.
Does it not want to show up today, or?
No, it's gonna show up tomorrow.
There we go. I was too high. I was too low.
Too high.
So, let me actually scroll over a little bit more. I'm gonna make this resistors.
Yeah, sine wave.
So resistors. Resistors resist current flow. It's a shocker. And that was also not a pun.
Yeah, I didn't think it was a joke until you said that was not a pun.
Well, no, the shocker part was the thing I was saying was not, that was the unintended pun.
Really shocking how this subject gets.
But yeah, so resistors resist current flow. That's their whole purpose.
I would hope so.
Most of the time, resistors are just wound up wires. So that's why when you see the symbol for resistor,
Oils.
So this is just a wire. A lot of times you'll see a resistor drawn like this. Same length of wire, but there's a bunch of squiggles in it to make the current, instead of it going like this, be like, oh, like this is a nice trip. It has to go up, and then back down, and then up, and then down, and then up, and then down, and then up, and then down, and then it can go forward.
I would hope a resistor makes it harder for the electrons and protons to travel through to their destination.
So since that is the case, we use resistors to make circuits safer by
And not just explode.
reducing the current flow. So there's not much more to resistors other than like Ohm's law and how to calculate resistance and totals and stuff like that. But we already kind of went over Ohm's law. But here's where we can get into short circuits. I don't know what fell on this side of my... Oh,
Have you ever contacted any of your professors?
I have
since
not.
College?
I have not contacted any professors since college. I could. I just don't really have a need to. And I'm also busy a lot, so I don't randomly wake up one day and be like, you know, I should email Dr. Hudson. Let me email him real quick. That's just not something that happens, like, at all. But shout out to you, Dr. Hudson. You taught me everything I know, for the most part. And Dr. Bosshart. Shout out to you as well. Not to brag or anything, but I was one of Dr. Bosshart's favorite students. It's probably a lie, but he did ask me one time if I wanted to take an exam, one of his exams, after I'd already passed the class. Jokingly, of course. And I said, no, nah, I'm good. That's how he knew I was smart, because I didn't want to take his exam again. But yeah, short circuits.
You didn't want to take another exam because you already passed it. Like,
exactly. I'm not trying to embarrass myself
no
in front of people that haven't taken the class yet. Anyway, short circuits. A lot of people think short circuits are literally zero resistance.
Isn't it like... Oh. Never mind. You go ahead.
This is false. Do not believe this. If anybody tells you that, they're lying or they're very uneducated. This is not true. A short circuit is not always zero resistance. Burn that in your skulls, burn that in your brains. That is a falsehood, a false statement. Okay? We're good? Okay, great. A short circuit is any resistance less than what is expected.
Alright, so I'm assuming there's a difference between expected and actual.
Well, yes, there's a difference between expected and actual. Come on, thing. Thank you. There's a difference between expected and actual, but when I say expected, I mean like within reason. So like as an example, if I have a 10K resistor, oops, drew it wrong.
And it's only resisting
and
9K.
let's say it's within a 2% tolerance. 1% tolerance, because that makes it easier for me. That means I get 100 ohms plus or minus. Yes, I get plus or minus 100 ohms of resistance to play with. So if I have a 10K resistor and it's reading like 10.0 wait, no, if I have 10.04K. This is good. This is a good resistor. This is a good resistor. 10.04K, good resistor. If I have a resistor that's reading 9.95K, this is also a good resistor. But if I come to the point in the circuit where I have 4K,
Oh, that's not good.
this is a short. Current is being sunk through this. So when you have a short circuit, because like Crim's or not Crim, like Skull's meme that he posted, low voltage. Path of least resistance. So like Skull pointed out, path least resistance with low voltage. The same thing applies. So if I'm supposed to be running a circuit where like I have, for example, if I have this 4K that's supposed to be a 10K, and I have, let's say, something that's supposed to be like a 6K resistor that's supposed to be running something else in the circuit that's more important than this 4K, or that's more important than the supposed 10K. So the blue is what's actually happening, the purple is what's actually happening, the white is what's expected. If I have this, I'm shorting the current that should be going here, and I'm going to try and use like a different color. The current that should be going here is actually getting sunk through here. And so I'm losing current, and it's getting sunk through here because it's less resistive. It's the shorter path. That's how short circuits actually work. The reason people tend to think it's zero resistance, which is actually an impossible thing for things to happen, because if you have literally zero resistance, there is no current flow. If there is zero resistance, there is no current flow. Because let's go back to our first thing that I told you guys. Do you remember that? Do you guys remember that from over an hour ago?
I don't know if I was here for an hour ago.
If there's zero resistance, there is no voltage. If there's zero resistance, there's an infinite current flow, which is not, it doesn't exist. It can't happen. It would essentially come out to 2 over 0, which does not exist. It's undefined. So that's why you can't have zero resistance. Now you can have very close to zero resistance, which creates a massive voltage and a massive current, because if I have 1 micro ohm of resistance over 1 volt, can you imagine how much current I have? Pretty much 100,000 amps.
Hey.
That's why low resistance is dangerous. Like I said, resistance is dangerous when it's low. It's almost like I know this stuff. There's dead Timmy. Anyway. So a short circuit is any time that the resistance is lower than what is expected. In most cases that you'll encounter in this classroom setting, a short is equal to 0. In real life, a short is less than expected. That's one of the things I had to no, I drew this backward. Um, I learned this the hard way when I first started my job this year. Because my electrical engineering mentor or my engineering mentor kept constantly saying like, you might have a short here, 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 and I'm reading 200 ohms as the short. But then you think about a capacitor is supposed to be almost infinite resistance. If it's an open, it's almost infinite resistance. So why am I getting 200 ohms across a capacitor? That's a short. Not zero, less than expected. I think this is a good place to end the studies and teaching here. Most people in college can't even focus for an hour and a half, much less people on the internet that are just barely interested in the subject. And I've been talking for an hour and a half about this stuff. But we have
I am very interested.
And also, you hit a point where like your brain is at capacity. But look how much we did. This is a lot of stuff that a lot of people have to learn. And if I were to teach like this, to actually teach electrical engineering, I'd have to go back and study all my old stuff, which I don't mind doing if you guys actually genuinely want to learn about more engineering topics. I'll put a poll up at some point, asking if anyone's actually interested in me continuing this, and if like I get like 5 or 6 yeses, then I'll continue it, like on a consistent basis. But this is stuff that takes people 4 to 5 months to learn in depth, and I taught you as much as I could in an hour and a half. There's still so much more to learn, but I'm gonna go ahead and pack it up for the day, because this, as much fun as I have doing this, I wanna relax my brain a little bit. So with that being said, I want to say thank you guys so much for watching this video in the stream. If you liked it, strike that like button like lightning.
That's shocking.
Sorry, I had to give you all a little electrical pun. But subscribe today to join the Shinobi, join the Discord, and I will see all you guys in the next one. Have a great night, y'all.